It's usually not a good sign to start anything out with a bunch of disclaimers, but since I use data borrowed from Hodgdon's online database, and they felt it necessary to put their disclaimers up in the front, I should probably do the same. I provided them for you, but they're also available at Hodgdon on their online source. It should be noted that they point out that when you mix primers, when don't mix powders, don't mix primers, don't mix bullets, that the low data they have generated was generated under very strict scientific controls, and that anytime you modify or deviate from anything, you're adding risk. In fact, that even if they have a bad lot, you're still taking their data, everything online as it is. And I would encourage you to pause the video and read their disclaimer before going any further. This video clip originates from Georgia Department of Natural Resources on their 2000 Hunter Education CD. It illustrates the burning rate of modern smokeless powder and that of black powder. You'll be able to determine the difference. That burn rate demonstration is a little bit misleading in that the amount of energy contained within a chemical, grain per grain or pound per pound, is not relative to the speed to which it reacts. The old black powder reacts quite quickly, but it does not contain nearly the amount of energy, and it cannot generate the high pressures that modern smokeless powders do. In addition, it should be noted that what they show you is an open air burn, which is a completely different situation than when you burn a powder inside a closed fixed volume container that requires you to shove a bullet out of the barrel. Chemical reactions are not always the same at every given temperature and pressure. While burn rate is not indicative of the amount of energy available within a chemical compound, it does indicate a relative speed to which one compound will react compared to another. Here is Hodgdon's relative burn rate comparison chart. This is an important concept. I want to give it a little bit more time. Take powder A. Take a powder B. Let's call the first powder black powder, to the second powder let's make it a modern smokeless propellant. While we've seen on burn rate that black powder burns very, very quickly, we can see that some of the modern smokeless powders burn slower. They both, when they burn, they decompose into gases that take up space and volume. So let's put them in a pressure vessel and see what happens. Well, when both of them burn, both of them expand into gases. They decompose into gases. But the modern smokeless powder has the capability of expanding into much more gas that generates a much higher pressure than that of the black powder. In fact, you can actually rupture old guns, old chambers, by using a modern powder that generates too high a pressure. I'm trying to make the point that use of the wrong powder in the right application, or even the right powder incorrectly, can result in catastrophic failure and even death. Here are some examples of the three main forms that powder is available in. If there are any other forms, I'm really not familiar with, unless it be some sort of a mix. But if we look right here, we see an example of a shotgun powder, and it is in flake form. It's little flat pieces, little round flat pieces. We look at this spherical powder or ball powder, we see that it's made up of some very, very tiny grains. And it measures real well with volume displacement type of measurements, scoops, powder throws, that sort of thing. The shotgun powders also work off of volume, as you know, in the Hornady and many other people's reloading machine. They're done literally with little load bars and little cylinders of various size that make up a very close approximation. And the last form is extruded powder, and if the camera's picking it up, it looks like little tiny pieces of broken spaghetti. It doesn't measure as well by volume as the spherical powder, but it is very, very stable. It has to do with the technology. Generally, extruded powders are very stable in extremes of temperatures, whereas ball powders that are made with the old Olin technology have something in them that make them measure real well by making spheres, but they're a little bit more sensitive to temperature, and so extreme hot and extreme cold, you do get variation in its performance more so than with the extruded powders. The bullet mass effect. Let's look at Hodgdon's online data, reloading data for a fixed powder and a 30-06. Now here we see as the bullets, the lowest bullet is 175 grain, the biggest bullet is 250 grain. So as we increase the bullet mass, what happens to the pressures? Well, we see the pressures increase. Now why is that? That's largely because for a given bullet diameter, like 308 as 30-06 has, to get a heavier massed bullet, you must have a longer bullet. And a longer bullet means not only more inertia because there's more mass, more lead there, but there's also more contact with the lands and groove. Another explanation may be that when the powder burns, it produces gases. These gases are expanding and taking up space. Where's the space come from? It comes from initially from the cartridge itself, but then as the bullet moves, as the bullet opens up volume behind it, it produces a total net increase in volume available for the gases to expand into. Well, light bullets move faster, and so they expand faster. So the volume available for that gas to take up increases faster than for heavy bullets, and so you don't see as high of a peak in smaller, lighter bullets that you do on the slower moving heavy bullets. The pressures will peak more with a heavy massed bullet. So as the bullet mass increases, let's look to see what happens to the charge weight. How much powder can we actually put in? Well, the previous explanation I hope made sense to you why the pressure goes up. But when you consider that the pressure is generally a limiting factor, the lower pressure available to the lighter bullets will also mean that you can use a little bit more powder behind the lighter bullets because they're naturally producing less pressure. So now you can put a few more grains in there for the same amount of pressure that you would have for a big, heavy, fat bullet. And that's one of the reasons why small bullets also go faster, because there's often more charge behind it. So there's multiple effects going on at any one time in these things. It's not as simple as if A, then B.